Hi everyone, welcome to week 3, the mathematics seminar. We've done sequences and SURDS so far. We're going to go into a bit more detail with SURDS, but first we're going to go back a little bit because some of you expressed that you wanted to go back over some things, like even things like factorizing. Make sure everyone's on the same page. I'm not going to spend too much time. We're going to do quite the easy, going over the basics of factorizing, polynomials, powers, indices, and then we'll come back and we'll do some more complicated SURDS. So to start with factorizing, simplest, we all learned in probably grade 7. Henry, how do we factorize that? Not factorizing, sorry, expanding.
Just 6a plus 10.
Plus 10, yeah, perfect. If we're going to do, again, a bit more complicated, minus 2y, bracket 2x. We're just kind of making these up. So we just have minus 4xy
Plus 14y squared.
We've got minus and minus, minus and minus, flip them around and make a plus.
Isn't it 14y squared?
Yes, it will be 14y squared. So you've got y and y. Perfect. Dry. Well, this should hopefully be simple revision for everybody. But most of the time when I see students caught up with methods and even general, it's because they've forgotten about all the basic stuff that you have to do. So now we've got a double bracket. Do they ever teach you about the FOIL method?
No, I haven't heard of the FOIL method, but I may have been told it as a different name.
Yeah, so you do, it's first. So you've got x times x. So we've got x squared outside, which is x times 2. So we have minus, we've got plus and minus, we have minus 2x. Then we've got inside 5 times x. Then we've got L, which is last, 5 times 2. Because we've got plus and minus, it ends up being a minus. That's how I'll do factorizing, and that's how I teach factorizing with a double bracket. Again, should be nice, simple revision for you guys. I want everybody, I'm going to write one up. Remember that method: first, outside, inside, last. I'll give everyone 30 seconds to 60 seconds to do that one using that FOIL method. Can't go wrong. I've got 60 seconds to do this one. I'm not going to spend too much time going over all this information, but I want to cover everything. What do we got, Henry?
X squared minus 4x plus 3x minus 12, which simplifies down to x squared minus x minus 12.
Perfect. So we've got x times x squared minus 4x plus 3x minus 12. We need to simplify that down to x squared minus x minus 12. We don't ever write 1x. It's implied that it's just 1. All right. Smash it through that. Powers and roots is what catches everybody up. So multiplication law. We've got we have AB times by AC. What do we do to the powers?
It's a to the power of b plus c.
Perfect. What about if we had x to the power of minus m times x to the power of n? What would we do there with the negative numbers?
Oh, you just do. Oh, it's 1 over xmn. Is that right?
I would just do x n minus m.
Oh yeah, I'm thinking of something else.
Yeah, I think you're thinking too much. This is like probably grade 10A stuff. What about fractional powers? So if we've got x to the power of 1/3 times x to the power of 1/6. What will we do then?
Oh, you just. It would become 3x to the power of 3 over 6.
Yeah, x to the power of 3 over 6. Because we can't have. And we would then simplify that down again. X to the power of 1 over 2. Or x to the power of half. Sweet. All good with that. We've got the division law. So if we had a power of b divided by a to the power of c, what would we have then?
A to the power of b minus c.
Perfect. So we then have, so to give an example, if we had x to the power of 6 divided by x squared, that would give us x to the power of 6 divided by x to the power of 2.
Which equals x to the power of 4.
We then have 6 minus 2, x to the power of 4. Perfect. What about when we raise one power to another? So if we have a, we'll sign a bracket, power of b, and we've got the bracket to the power of c.
It equals a to the power of bc. You times them.
Perfect, yeah. Well done. What about to the power of 0?
It always equals 1.
Should always equal 1. So
Yeah.
a to the power of 0
Is 1.
always equals 1. Anything to the power of 0. 100 to the power of 0 equals 1. X to the power of 0 and doesn't matter. What about power 1? So if I have a to the power of 1, what would that equal?
A to the power of 1, just a.
It'd just be a. 100 to the power of 1 would be 100. Doesn't really matter what it is. What about 1 to the power of anything?
1. It's just always 1.
Yeah, so 1 to the power of 1 is the same as 1 times 1, always equals 1. 1 to the power of 100 still equals 100. 1 times 1, 100 times, which is still just going to be 1. What else we got? What about fractions? Everybody's favorite is fraction. So if we were writing it just in pure algebraic form, we have this. So if we were to put that into numbers, So we have 2 3/4 to the power of 5. What would that equal?
3 to the power of 5 over 4 to the power of 5. I don't know what that is off the top of my head. 3 to 3 is 27.
So we have 2 times 3 gives us 6. Then we add the 5 to it. We add the power of 5. So it'll be 11 over 4. Still to the power of 5. And then we would just bring our power inside the brackets. Our multiplication rules. All good?
Yep.
Perfect. This should be a revision for you, but good for the rest of them to go over. Grade 10. So now we've got roots. We're used to square roots, right? So 4 to the power of 2 equals 16. But 2 square root of 16 equals 4. So here we've got the square root. And we can do the inverse of that. And we go back to 4 squared. We also have cube roots. So we have 2 to the power of 3 gives us 8. Again, we do the inverse of that. Gives us 2. And the reason we put the numbers here, because that tells us if it's a square root, cube root, 4, 5, 6, 7, 8, 9, up to infinity. So you have to make clear when you're writing, doing square roots and cube roots. If it's square root, you've got a 2. If it's cube root, If we've got 4th root, shock horror, we will put 4 there. So on and so forth. So if we were to look at some simplification, how are we doing for time? We're doing all right. With our multiplication, we have 5p squared q cubed times 3p q to the power of 4. All right. If you're watching the recording, Henry, have a go at this. Take 60 seconds. Should be fairly simple if you follow the like term rules. This is just hoping to put all those laws and rules we just looked at into practice. So I'm just going to start writing it out. Hopefully Henry's ahead of me. So we want to separate this out so that we can look at the like terms. So we would have 5 times p squared times q cubed times 3 times p times q to the power of 4. 5 times 3. Hope we all know that equals 15. P squared times P. We know from our multiplication rules, sorry, it's meant to be a square there. We add the P, we add the powers, so it'll be P3, P cubed. Same here, we've got Q to the power of 3 times Q to the power of 4. What would that give us, Henry?
Q7.
Q to the power of 7. Sweet. So we will put that back together. 15 P to the power of 3, Q to the power of 7. That's how we simplify using those rules. We'll practice a division. So we've got 3 to the power of 4 times 3 to the power of 7 divided by 3 to the power of 8. So again, give you guys 45 seconds. My voice is holding out much better. All right, so what we do is we do multiplication first. So 3 to the power of 4 times 3 to the power of 7 gives us 3, and then we add the powers. So we've got 3 to the power of 11. So we can rewrite the equation as 3 to the power of 11 over 3 to the power of 8. What do we do with division?
Minus.
We take them away. So we have 3 to the power of 11. Take away 3 to the power of 8. We have 3 to the power of 3.
Which equals 27.
We get 27. Perfect. All right, let's move on from that. Who remembers their indice rules? This is what you always see with method students. They forget these basics. So they understand the methods concept, but putting the actual answer together. So if we're looking at indices rules, moving on now, we're going to fractional powers. So A to the power of B over C would be the equivalent of the square root of C, A to the power of B. So this is when we're trying to figure out square and cube roots. So if we had x to the power of half, how would we display that as a square root?
The square root of x to the power of 1, which is just x, and then outside the thing is 2.
Exactly like that. Perfect. What about if we had x to the power of 1/3? Would then be the cube root, wouldn't it?
It would just be it'd be in the brackets just x, and then outside the brackets
3.
3.
Perfect. So if you've got a fractional power, we want it as a cube root or a square root. Because when we're doing complex calculations, we don't want fractions. We want whole numbers. We don't want any kind of rounding. We don't want any kind of, that's why we do SURDS, right? Let's make it a bit more complicated and make it a multi-step fractional power. So if we had 64 to the power of 2/3. How could we figure out, how could we solve that?
You'd get square root of 64.
Would it be the square root or the cube root?
Oh, it'd be the cube root.
Yeah.
It'd be the cubed root of 64 squared.
Which would be,
I don't know what 64 squared is.
well, we could just change it to the cube root of 64.
Oh, can we get rid of the 2?
So then we'd have 4. Then we add the squared in down here because it's much easier, which would give us 16.
Oh, so the cubed root of 64 squared is?
Yeah, the same as 4 squared. Just easier to add it down here because 64 times 64, I can't bother working it out. And if you were putting in your calculator the cube root of 64 squared, you'd probably get 16. I'd guess. All right, so a little bit more on this. Negative powers. So a to the power of negative b. I'll be really impressed if you remember how to do this, Henry.
Equals 1 divided by a to the b.
Perfect. Because we don't like having
Is it a b or a to the power?
a to the power of b. I just wrote the b too big, sorry. A to the power of b. So if we were to put this as a to the power of -1.
It's 1 divided by a.
Yep. Or 10 to the power of -1. Why do we do that? What does it do to the power? It makes a positive number.
Yeah.
Yeah, that's why we do that, because we don't want to have negative numbers. What else? We can also have negative numbers, negative powers in a fraction. So a over b to the power of -x. We would flip, all we do here is flip the numerator and the denominator. This one catches lots of people out. B over a. And by doing that, it becomes to the power of x. So if you have a fraction and a negative power, flip the numerator and the denominator and it changes it from negative to positive. All right, a couple of practice questions again. We've got 4 to the power of -3. I'm going to give you guys 45 seconds again. So if we flip this around, 4 to the power of -3 is equal to 1 divided by 4 to the power of 3. We can get rid of the 1 divided by because it's always going to equal the number. 4 to the power of 3 is 64. Or 1 1 over 64. If you were going to put that into a surd, Henry, what would it be?
1 over the square root of 8, which then you can simplify down to the square root of 2 times the square root, square root of 4 plus the square root of 4, I think.
Yes. Yeah.
Which, no, times the square root of 4 times the square root of 4, which then you can get 2
plus
2 root, no, which just equals 4.
Yeah. So 2 square plus 2 square, which would just be 4. Perfect. All right. You got a good picture of it in your head and how it all syncs together. All right, fractional powers. How will we solve 9 to the power of 2 over 3?
It becomes the square, it becomes the cubed root of 9 squared. So you just do this cubed root of 9, which means you get, no, we'll do 9 squared because we know what 9 squared is.
Yeah,
I do the cubed root of 81. Oh, can you? I thought
because the square root of 9 is 3. Or which would then become 3 to the power of 3.
I thought the bottom number in the fraction became like outside and the top number became inside.
Unless I've written around the wrong way. Yeah, I've got them written around the wrong way. Sorry, I'm just
okay. Yeah, I did the square root of 9 cubed. So you just do the square root of 9, then to the power of that, so it's 27.
Perfect. All right. Let's mix it all together just for fun. Make sure everybody understands. Because, I mean, knowing all the individual concepts in maths is great, but it's knowing how to put them all together. So we have 2 to the power of 15 times 8 to the power of negative 4 as a power of 2. No calculators for this one.
As a power. So we'll end up with
So we know that 8 is 2 to the power of 3. So we can actually rewrite this in a slightly different way. 8 to the power of minus 4 equals 2 cubed to the power of minus 4.
and then it's just 2 to the power of 3. Yeah, it's 2 to the power of 3. Is 8. Is that the correct answer?
So
I got 2 to the power of 3 as the final answer.
2 to the power of 3.
Which is 8.
8. Perfect. All right. Voice is held out longer than I thought. We're going to get into the quadratics and stuff once everybody is in. Okay, surds. Multiplying surds. Again, this might be a bit of revision from last week, but we're going to go through. Would just equal square root of a times b, right? So if we have square root of 7 times the square root of 2. So now we're looking at surds again. We're going to go a little bit in depth if my voice can hold out. Gives us the square root of 7 times 2, or the square root of 14. If we're dividing surds, again, we do pretty much the same thing. We've got square root of A divided by square root of B. We simplify that by square root of A over B. So if we change this to 10 and 5, we get up the square root of 2. Adding and subtracting. Everybody gets confused because they go, oh, it's just the same as multiplying and division. What do we do when we add or subtract, Henry?
When you're adding and subtracting, you I don't think I have. I don't think I had that rule.
So if we have we would just have 3 to the square root of B. Do not just go, oh, the square root of A plus the square root of B gives us square root of A plus B. That's not correct. What if we simplify them? We use surds because they're whole numbers. We're not going to get any rounding errors. If you're doing massive calculations, you don't want to be rounding. So simplifying, square root of 28, what will we get there?
You can break it down into square root of 4 and 7.
Yep, so square root of 4 times 7.
So then you can do the square root of 2.
Square root of 4 times the square root of 7.
Yeah, and then from there you can break down the 4 into the square root of 2, square root of 2, which just equals 2. So you get 2 times the square root of 7, and that will be your final answer.
2 times the square root of 7.
Yeah.
Perfect. We're going to go a little bit more in depth with the surds now, looking at double brackets. So if we have n plus n plus the power of n, how would we solve that? Remember that FOIL method? First, outside, inside, last.
We do m squared.
Yep, so we have m squared, we've got n times m.
And then plus m times the square root of n.
Yep.
Plus m times the square root of n. And then plus n squared, which just equals 2 n.
Yeah. Plus n. Can we make that any smaller?
You get 2 equals m squared plus 2 times the square root of n times m.
So we have m squared.
And then plus 2 times 2m to the power of n. And then plus
So really, when you're looking at surds and double brackets, it doesn't really change.
Yeah.
You're using the same concepts. Let's see if we can put it together. I'll give you a complicated one out of my head. I mean, not hugely complicated. Still keeping it pretty light for the first couple of weeks. And we'll get real painful. So again, what do you guys have to go with that one? Give you 60 seconds, no pressure.
I got 7.
Perfect. So we would have 10 to the power of 2 minus excuse my terrible not moving myself enough room on the board. Was that your first line, Henry?
Yes.
And then we have 10 minus,
The square root of 30 plus the square root of 30.
perfect. So that would give us 10 minus 3.
Yes. And then that equals 7.
And then 7, perfect. 30 minus 3. 10 minus 3 is 7. Perfect. What about rationalizing the denominator? So when we've got a to the power of square root of, a divided by square root of b. How would we flip it around or rationalize the denominator?
Would you do?
Don't overthink it. So will we not just times numerator and denominator by square root of b?
Yeah.
Which gives us, then we have a to the square root of b divided by. That's not meant to be 6. All right, let's make it a little bit harder. Again, I want to give you guys a chance to do it, and then we can go through answer. What I want you to do, if you're watching the recording or if you're watching it live, is make note of anything that you're not sure of and ask me any questions or ask me to go over anything again. So how would we rationalize the denominator here?
You would, because do the square roots cancel out each other?
Should do, yeah.
Not do that. Okay.
So then we would basically times both sides by 3 minus square root of 5.
Yeah, and then you'd get 15.
So the next line we'd have 5, 3 to the power of minus square root of 5 over
3 times. 3 plus square root of 5 times 3 minus the square root of
3. So the next line we'd have 15 minus 5 power of 5. Remember we've got double brackets.
Yeah.
So we have 9 minus
3 squared minus 5.
Plus 3 minus 5. So the reason I'm going back through even this like simple algebra stuff before this is that in order to get questions like this right, you have to remember those rules. So then we have 15 minus 5 square root of 5 over 9 minus 5. So we then just have, I'm not going to rewrite that because is that the answer you got, Henry?
Yeah, that's what I got.
Yeah. So that's a bit more complicated. Not quite as simple as just flipping them around, but it's exactly the same concept. We've got double brackets where we've got surds. You just follow the basic principles of expanding the brackets that you learned way back in grade 7. And that is all that most of senior maths is. It's putting together everything you've already learned, but doing it to answer a question. The best and brightest students don't always do really well in methods and specialists because it requires a different way of thinking. So when we're talking about rationalizing the denominator, we're actually talking about getting rid of the surd, right? So we've got 3 over square root of 5. And basically what we want to do, we want to have a rational number underneath. Or we're rationalizing, taking it away from being a surd to being a rational number. So we times top and bottom by square root of 5, which gives us 3 square root of 5 over square root of 5 square root of 5. We remember back to our surds and multiplication rules. Square root of 5 square root of 5 gives us square root of 25. I was trying to do it in really stepping it out, so everyone.
I have the rule written down: square root of a times square root of a equals a.
Yeah, so if we do that, equals 5.
Oh yeah, the square root of 25 is 5. Yeah.
Yeah. So we then have 3 to the power of 5 over square root of 5 square root of 5, which just gives us 3 to the power of 5 over 5. 5 is a rational number. So we've successfully rationalized the denominator, whereas before it was a surd. Maths and science, very logical with the names. Don't know how much further to go. Let's do one more. Last one that I've got. So rationalizing a surd. We'll do another one. So now we have 8. I'll give you guys 2 minutes to figure this one out. Okay. So we would end up having, we have times again. What we need to do, because this is a type 2 question, we have to turn the plus into a negative. So we take it, we times by 5 to the power of minus square root of 2. So that gives us our double brackets on the bottom, up here. 8, sorry. So we've got top line, we're just adding so down here, got 5 plus square root of 2. Then over the other side, we want to have minus. So 5 minus square root of 2. So what we want to do here is end up with a surd on top and a rational number on bottom. So the top line here, I need a bigger whiteboard. 8. So then this up here is equivalent to 8 times 5 for putting like terms together, plus 8 times minus square root of 2. This is on the top here. So that would give us 40. So now at the top we would have 40 minus 8 times square root of 2. The denominator, we want this to be a surd, sweet. Underneath, we do not want it, we want it to be a rational number. Henry, how did you calculate the denominator?
I did 5 times 5 is 25.
Yeah.
And then because your one's plus, one's minus, they cancel out.
Yeah.
So then you just left with the root 2 times root 2, which is just 2. And because plus times a minus is negative, so it's just 25 minus 2, which is 23. So you end up with 40 minus 8 times root 2 over 23.
Perfect. So here we've got 5, we've got plus 5 to the 5 times square root of 2 and a negative. So they just cancel each other out. So we would just have 5 squared minus 2 gives us 23. And I'm going to leave it there because my voice is gone. We've covered what I think are all the basics now. And I think now we can work into log laws and all that fun stuff. Start looking at some hardcore graphing. Most of this will be non-calculator this time. I haven't quite figured out how we would integrate computer stuff, calculator stuff into this. I'm sure there's a really good app online that we could use to screen share, but we'll figure that out at a later time. I will see you guys next week. See ya.
Okay, thank you, Liam.
Have a great day.